In this online lecture, we're going to discuss some of the concepts that we should have learned in general chemistry concerning equilibrium. And let me remind you how this works. Let's say you have a reactant A that's going to turn into a product B. But let's say this reaction is reversible, which means B can also break down and turn back into A. Let's think about this on a molecular level here. Let's say you have, for instance, 4 A molecules. What we're saying is that each A molecule could potentially turn into B. So let's say one of them turns into B, let's say another one, and let's say even a third one could turn into B. Then what's going to happen simply is that B, remember, can turn back into A. So as time progresses, we can expect B to go back into A like this, maybe one of these B's, and then let's say maybe another like this. And then this process repeats itself. Then A's start turning back into B's and so on. But what happens is eventually is that the rate of B formation and A formation levels off. What that simply means is that there's no net gain of A or B. Or in other words, let's say in this case, the amount of B's here are 3 and the amount of A's are 1. At equilibrium, the concentration or amount of A and B level off. And let's say for our particular reaction, this is what equilibrium would happen to look like. And imagine this. Let's say you take the amount of B, which is 3 right here, and divide it by the amount of A. 3 divided by 1 is simply 3. What we need to understand here is that this would be a constant, meaning that this wouldn't depend upon any amount of A or B. When this reaction is at equilibrium, there's always going to be 3 B's for every 1 A. And let me show that to you here, just to make sure you got this. Let's say, for instance, instead of starting with 4 A's, we start here with 8 A's. Then we know, for instance, some of the A's will start turning into B's. And of course, B's will start turning into A's. But eventually, this reaction is going to reach equilibrium. And remember, that means there's going to be no net A or net B formed. In other words, the amount of B's and A's are going to start to level off. And for this particular reaction, this is what equilibrium would look like. You would have, for instance, 6 B's and 2 A's. Why is this so? Well, remember, if we do this again, if we divide the number of B's by the number of A's, in this case, 6 divided by 2, you're going to get that constant again, 3. Because remember, 3 tells us for every 1 A, there are going to be 3 B's at equilibrium. Just like for every one of these A's right here, there's going to be 3 B's. So notice here, taking the amount of products and dividing them by the amount of reactants always yields a constant value. And that constant value is called KEQ. So, for instance, we would say the KEQ for our A to B reaction is equal to 3. This is a very valuable tool in general chemistry and in organic chemistry. But before we talk about all the value we get out of this, let's remind ourselves how to generate a KEQ for a particular reaction. Let's say this generic reaction right here. If you remember from general chemistry, we have to follow certain rules to generate the KEQ for this reaction. If you remember from general chem, the KEQ is the products over the reactants, raised to their corresponding coefficients. So for instance, notice C right here is a product, and lowercase c here is the number of C products. And if you remember, we always raise the amount of product to that coefficient. Also, I want to remind you is that in this expression, you only plug in aqueous, that is concentrations, and gases as partial pressures. We never put solids or liquids into the KEQ expression. But let's get a conceptual understanding of KEQ. We should know that if your KEQ value happens to be greater than 1, then think about what that means. If KEQ is products over reactants, then a value greater than 1 means at equilibrium, your concentration of products will be greater than your concentration of reactants. So at equilibrium, we're going to have more C than we would A and B. So having a KEQ greater than 1 means that the reaction is favorable from left to right. But what about the opposite here? What if your KEQ value is less than 1? Well, again, if we look at products over reactants, in this case, you're going to have a higher amount of reactants than you are products. So at the end of equilibrium, you have more A and B than you would have C. This, of course, would be called a non-favorable reaction. That's why this next equation here is so important. Notice on the left-hand side you have delta G, and on the right-hand side you have KEQ. This equation is so groundbreaking because it connects delta G, which is a thermodynamic topic, to KEQ, which is a reaction equilibrium topic. So we're bringing two worlds into one. And let me show you how they're linked together. Let's say, for instance, you have a KEQ that's greater than 1. Remember, we learned that that's a favorable reaction. Well, if you looked at the graph of natural log of KEQ, you would see that the natural log of anything greater than 1 is a positive value. So that means natural log of Q would be positive here. Temperature we would plug in. Remember, temperature is in Kelvin, which runs from 0 to infinity. There's no such thing as a negative temperature in Kelvin. So temperature would be positive. And R, this is a constant, would also be positive. That means because of this negative in the equation, plugging in a K value that's greater than 1 would give you a negative delta G value. And remember, we said a reaction that has a negative delta G value is favorable. And vice versa, if you plugged in a KEQ that was less than 1, then the natural log of that number is negative, which means in that case your delta G will be positive. And again, a K value less than 1 and a delta G value that's positive for a reaction means that that reaction is non-favorable.